Okay, so now we're going to introduce the concept of differentiability. We say that f of x is differentiable at a point c if the derivative at c, f prime of c, exists. And we also say that f of x is differentiable on an interval I if it is differentiable at every point c in I. And now differentiability is related to continuity in the following sense. If f of x is differentiable at a point or on an interval, then it is also continuous at that point or on that interval. Okay. Let's note that f of x can be continuous but not differentiable. So differentiability implies continuity but not the other way around. The prototypical example of this is the absolute value function. F of x is equal to the absolute value of x. For positive values of x, f of x is just equal to the function x, which is a line with constant slope 1. So its derivative, which is the slope of the line, is 1 for all x greater than 0. F of x is equal to negative x for x less than 0, which is a line of slope negative 1, so the derivative is negative 1 for x less than 0. However, at 0, when we try to evaluate the derivative at 0 using the definition, we get f of 0 plus h minus f of 0 over h. F is the absolute value, so we have the absolute value of 0 plus h minus the absolute value of 0 over h. 0 plus h is just h, and the absolute value of 0 is 0. So we're left with the limit as h goes to 0 of the absolute value of h over h. We've looked at this limit before. From the right, this limit is 1. From the left, this limit is negative 1. So the limit does not exist, and the derivative of the absolute value does not exist at 0. However, we've also shown that the absolute value is continuous at 0. The limit as we approach 0 is indeed equal to 0. So this function is continuous at 0, but not differentiable there. So how can a function fail to be differentiable? Well, first of all, since differentiability implies continuity, if we have a discontinuity at a point, we can't be differentiable at that point. Okay. Well, what about places where we are continuous but aren't differentiable? One possibility is a corner or a cusp. So this is what I would call a corner, where a curve comes and two pieces of it meet at a sharp angle. Or a cusp is when they come in almost to like a little point, like this picture. Try to imagine a tangent line here. Since it's a point, I can actually move a tangent line all over the place. So, same thing over here. There is not really a unique tangent line here. So we're really looking for points that have unique tangent lines. So these are not going to be differentiable. In these cases, also what often happens is the limit as we evaluate the derivative at this point, as we try to evaluate the derivative, will be one thing from one direction and something else from the other. We just saw that with the absolute value. From one direction, the derivative looked like negative 1. From the other, it looked like 1. So in that scenario, we're going to run into a function which is not differentiable because there really is not a unique tangent line. The last case where a function can fail to be differentiable is when it has a vertical tangent, like this graph right here. For example, y is the cube root of x has a vertical tangent at 0. Now this is really the worst, or the least bad out of these three possibilities, because the function here is still pretty nice. The only problem, has a tangent line. The only problem is we can't evaluate the slope of the tangent because it's vertical and it's undefined. However, in a sense, we will think of the slope of a vertical tangent as being infinite or negative infinite. It will, depending on the scenario, that might make sense. Now we have a number of different ways of denoting a derivative. The first one that we have seen are primes. We just put a little sort of an apostrophe after f. And if I just want to talk about the function f without talking about the variable x, I can just write down f prime, that's fine. And if we're given y as a function of x, we can write it as y prime. There's also something called Leibniz notation. Now, Leibniz was a German guy who came up with the calculus basically at the same time as Isaac Newton was coming up with it in England. And his notation looks something like this. We write d f of x over dx, and that is supposed to mean the derivative of f of x with respect to x. The thing is, sometimes you might be dealing with more than one variable, and it makes sense to start saying what is the variable that we're taking the derivative with respect to. We're going to run into that. Okay, now when you write df over dx, you could put the x right next to the f. You could also put it next to the fraction, like this, although we shouldn't really think of it as a fraction. Or you could just write df over dx, or if we're thinking of y as a function of x, we can write it as dy over dx. Again, don't think of this as a fraction. It kind of is. It's supposed to be reminiscent of the notation for a rate of change, delta y over delta x, but we shouldn't necessarily think of it as a fraction. In a sense, it says an infinitesimal change in y over an infinitesimal change in x, but for now, just think of it as notation. There are some other ways that we can sit down and try to write derivatives. Sometimes people just write a d in front of f, or they'll write d with a subscript x to say that they're taking the derivative with respect to x. You might run into this someplace. We're not going to use it. Mostly we'll be using these things. Typically the primes we will be using because it's simple notation. However, sometimes using our rules of differentiability, it's going to make more sense for us to use this Leibniz notation. Okay, so the derivative of f of x is itself a function. So now that we're thinking of the derivative as a function, that means that we can take the derivative of the derivative. This leads to higher order derivatives. So we're starting with the function f of x and we take its first derivative. That's a function, so we can take its derivative. We write that as f with two primes, or f double prime. We call that the second derivative, because we've taken two derivatives. The derivative of the second derivative is f with three primes, which we call the third derivative. Then there's the fourth derivative, the fifth derivative, etc. Eventually, you run out of primes, or I'm not going to write 10 primes in a row to talk about the 10th derivative. So one thing we often do is we will jump into Roman numerals. So the fourth derivative I'm writing as f with an IV up there to mean 4, and that's pretty good for small derivatives. But in general, if I want to write down the nth derivative, where n is some whole number, I'll write it as f with the superscript n in parentheses. And that's going to be the nth derivative, meaning I took n derivatives. So for example, if I write f 100 of x, and that's the 100th derivative of f, that means I start with f of x, I took a derivative, then another one, and after 100 iterations, I got down to this function. Some other notation, and I'm not going to use this a lot, if at all, but I'm just putting it up there for the sake of completeness. We can use Leibniz notation to do higher order derivatives. We can write d over dx thinking of it as an operator, which means I'm taking a function and producing another function with it. And I can raise it to the exponent n to suggest that I'm taking a derivative n times. I'll put that in front of f of x or in front of y. Or there's this more compact notation, all right, d to the n f over dx to the n of x, or d to the n y over dx to the n. These two are supposed to mean the nth derivative of f or the nth derivative of y. All right, let's do something that might seem a little bit crazy, but it actually is not. Let's find all of the higher order derivatives of f of x is x cubed minus x. Okay. Well, we already found out that f prime of x is 3x squared minus 1 from before. Now let's evaluate the second derivative. So I'm going to take f double prime of x is the limit as h goes to 0 of f prime of x plus h minus f prime of x all divided by h. I replace that with the formula for f prime of x. So I get 3 times x plus h squared minus 1 minus 3 times x squared minus 1 all over h. I multiply that out, and I get this lovely expression here. Take a minute to make sure I didn't mess up anything there. And then I combine my terms to get myself here, 6xh plus 3h squared. I divided the top by h, which leaves me with 6x plus 3h. And as h goes to 0, this approaches 6x. So the second derivative is 6x. Now, the third derivative is the derivative of the second derivative. The second derivative is 6x. 6x is a line. It's a line with slope 6. So the slope of every single secant is 6. So the slope of the tangent is 6. So the derivative of a line is simple. We already know that. It is the slope of the line. So the third derivative is 6. Now, the third derivative is a constant function, which means that its graph is a horizontal line. A horizontal line has slope 0 everywhere. So the fourth derivative is 0. That itself is a constant function, which is a horizontal line, so its derivative is 0. Every derivative after the fourth is 0. So whenever I have a polynomial like this, after a certain number of derivatives, all of them are 0. So here is question 3. Let's note that the acceleration is the rate of change of velocity, and velocity is the rate of change of position. Therefore, acceleration is the second derivative of position. So let's let s of t be 450 minus 4.9 t squared from an example we did before. Find the acceleration of t, and that is the second derivative of s of t.